1. What specific problem does NVILA aim to solve in the context of visual language models, and how does this problem relate to existing challenges in the field?
NVILA aims to solve the problem of inefficiency in visual language models, VLMs, which are often expensive to train, fine-tune, and deploy due to their high computational and memory requirements. Existing challenges include the time-consuming nature of training large models, the memory-intensive process of fine-tuning, and the resource constraints faced during deployment in edge applications. For instance, training a state-of-the-art 7B VLM can take up to 400 GPU days, and fine-tuning such models can require over 64 gigabytes of GPU memory, which is beyond the capacity of most consumer-level GPUs. NVILA addresses these issues through a scale-then-compress strategy that enhances both efficiency and accuracy, allowing for high-resolution image and long video processing while significantly reducing training costs, fine-tuning memory usage, and latency. By optimizing the entire lifecycle of VLMs, NVILA not only improves performance but also makes advanced VLM capabilities more accessible to researchers and practitioners.
2. Can you provide a detailed, step-by-step explanation of how NVILA works, including its architecture and the processes involved in scaling and compressing visual tokens?
NVILA operates on a scale-then-compress paradigm to enhance both efficiency and accuracy in visual language models, VLMs. The architecture consists of three main components: a visual encoder, SIG-LIP, a projector, a two-layer MLP, and a token processor, QEN2, of varying sizes. Initially, NVILA scales up the spatial and temporal resolutions of input images and videos to capture more detail, for instance, resizing images to 896 by 1896 and increasing the number of sampled frames from videos. Following this, NVILA compresses the visual tokens. For spatial compression, it employs a spatial-to-channel (STC) reshape to reduce token count by a factor of 4 while maintaining accuracy, and for temporal compression, it uses temporal averaging to pool visual tokens from consecutive frames, effectively reducing redundancy. This systematic approach allows NVILA to process high-resolution inputs efficiently, while achieving competitive performance across various benchmarks.
3. Illustrate the inner workings of NVILA by walking through a simple example, showing how an image or video input is processed through the model's architecture.
NVILA processes image or video inputs through a structured architecture comprising three main components: a visual encoder, a projector, and a token processor. For instance, when an image is inputted, the visual encoder, SIG-LIP, first extracts features from the image, which may be resized into multiple scales using the dynamic S2 method to maintain aspect ratios and enhance detail. These features are then aligned with language embeddings by the projector, which is a two-layer MLP. Finally, the token processor, typically an LLM like QEN2, takes both visual and language tokens as input and generates language tokens as output. This scale-then-compress approach allows NVILA to efficiently handle high-resolution images while compressing visual tokens to improve computational efficiency, ultimately leading to enhanced accuracy and performance across various benchmarks.
4. What are the notable theoretical and practical benefits of using NVILA compared to existing VLMs, specifically regarding efficiency and accuracy?
NVILA offers significant theoretical and practical benefits over existing VLMs by optimizing both efficiency and accuracy through its scale-then-compress strategy. Theoretically, NVILA enhances model architecture by scaling spatial and temporal resolutions, which preserves more details from visual inputs, thereby raising the accuracy upper bound. Practically, NVILA reduces training costs by 4.51 times and fine-tuning memory usage by 3.41 times, making it more accessible for researchers with limited resources. Additionally, NVILA achieves competitive or superior accuracy compared to leading open and proprietary VLMs across various benchmarks, demonstrating its effectiveness in real-world applications. Overall, NVILA's design enables it to process high-resolution images and long videos efficiently, while maintaining or improving accuracy, setting a new standard for VLM performance.
5. Describe the methodology used to validate NVILA's effectiveness. What datasets and benchmarks were used, and what key metrics were considered in the evaluation process?
To validate NVILA's effectiveness, the methodology involved comprehensive evaluations across a diverse range of image and video benchmarks. For image benchmarks, NVILA was tested on datasets such as AI2D, ChartQA, DOCVQA, Infographic VQA, MathVista, and others, where it demonstrated competitive performance against both open-source and proprietary models. In the video domain, NVILA was evaluated on benchmarks that included short and long videos, achieving state-of-the-art performance by processing up to 256 frames. Key metrics considered in the evaluation process included accuracy scores across various tasks, with specific attention to improvements in reasoning and knowledge benchmarks, as well as OCR capabilities. The results indicated that NVILA not only matched but often surpassed the performance of leading models, showcasing its efficiency and effectiveness in handling both image and video data.
6. What limitations or constraints does NVILA face in its implementation, particularly in the context of specialized domains like medical imaging or robotics?
NVILA faces several limitations in its implementation, particularly when applied to specialized domains like medical imaging and robotics. Firstly, while NVILA optimizes efficiency and accuracy, fine-tuning for specialized tasks remains memory-intensive. For instance, fully fine-tuning A7B VLM can require over 64 gigabytes of GPU memory, which exceeds the capacity of most consumer-level GPUs. Additionally, the model's architecture, although designed to handle high-resolution images and long videos, may still struggle with the unique requirements of specialized domains that demand precise interpretations of complex visual data. Furthermore, the need for domain-specific vocabulary and concepts necessitates careful tuning of learning rates and model components, which can complicate the fine-tuning process. Lastly, while NVILA introduces capabilities for tasks like robotic navigation, the integration of multi-frame inputs and real-time processing may still be constrained by the computational budgets of edge devices, limiting its deployment in resource-constrained environments.